Imagine I have this cone here and I roll it like this is so point at the bottom. This point is touching the floor and I roll it around and now it's like this. Well, it's rolled around, you get the point. Basically, if it does one full roll, it's going to leave behind an area, right? So the cone did one full roll and this is the region it covered after doing one full roll. Let's put this point here. So this blue point went all the way across. This green part, it looks like this. Let's call the vertex of the cone P. This is the pointy edge. And let's call this radius R. And this arc over here, they're equidistant from the point P. So this same distance. So basically this is a sector of a circle. Like this. And let's say this is theta in radians, and this arc length is the same as the circumference of the circle because this did one full roll over here. So this circumference, this here, is equal to the circumference of the circle, and it is C is pi L. L is this. L is also the slant height of the cone. This is L, right? The slant height of the cone. Since rolling the cone covered this area, the surface area of this green part would be the lateral surface area of the cone. The surface area, this green part would be the lateral surface area of the cone. And in radians it would be the surface area of the entire circle is pi L. Like if this was a full circle, it would be pi L squared, but we only want a fraction of it, which is theta over 2 pi. So this is half L squared theta. Also this circumference is pi r squared, where r is the radius of the bottom of the cone. So circumference is pi r squared. So putting the two together, can write it like this. Then I can put this over here. Whoops, wait, hold on, I made a mistake. Circumference of this circle here is 2 pi r. So the lateral surface area of the cone is pi L r. Excellent. Now I'm going to introduce another shape called a frustrum. So frustrum is like a piece of solid enclosed between two parallel planes. So over here this is a frustrum. Let's call this R1. Let's call this R2. Sorry, my drawing is not perfect. Let's call this entire thing L, and let's call just this thing D, and then this over here is L minus D. So I want the surface area of just the frustrum. Surface area of the frustrum only would be lateral surface area of the large cone minus the lateral surface area of the small cone. So that would be pi R2L minus pi R1 L minus D. R2 is the largest, so wait. D. R1 R2. Now I have this surface area, but I only want it in terms of R2, R1 and D. I don't want any L over here. So what I can do is, since let's say we have a cross section of the cone R2, R1, and all this is L, and this part this part is L minus D, this part is D. And since the radius is proportional to the slant height, I can write R2. So R2 over L should be equal to R1 over L minus D, since the radius is proportional to the slant height. Which means right? I hope I'm right. So L is D times R2 upon R2 minus R1. Now going back to the surface area, I can replace L, right? Surface area is pi D R2 squared R2 minus R1. Then I can replace this as minus and dr1 I can do this. Wait a minute. Whoops, I forgot D here. Right now I can take D out. And this is going to be annoying. So I can multiply d is outside, and I can multiply these two, and I can separate the fractions as well. r1 squared r2 minus r1, right? And then this and this cancel out. r2 squared r1 squared r2 minus r1. Now, so j plus k times it by j minus k. Like I'm just showing you something and then I'll get back to this. This gives j square minus jk plus jk. K minus k square. Which means j plus k, so j square minus k square over j minus k. That this makes sense, right? So going back, I can write it like this: pi d and both the radius. This is the lateral surface area of a frustum of this shape. So now, why did I derive this? So basically, we have a graph. If we want to find the arc length, we can take this, draw two lines, right? And then revolve this around and find the surface area of this using the formula for frustrum. So what I can do is, let's go back here, like this. So yeah, see what they're doing here is taking one line segment, revolving it around, and then they're calculating the surface area of one of these bands. So surface area of one band, so band is like these strips, so revolving one of these strips will give a frustrum. The surface area of one of these frustrum is, so let's say in terms of xi, I is the front one, so radius of the one at the back, the two f values at xi minus 1 and xi times it by the line segment, this diagonal line, and let's call this times it by square root. So what I did here was, we zoom into the curve, we had delta x is the same for all of the bands, so delta x and delta y would be different. So this squared plus this squared will give you the diagonal line squared. So this is the length of the diagonal line. If I take delta x out, I can take delta x out, so I'm left with 1 delta yi delta x squared. Yeah, because I took the delta x out. And for this, if according to the mean value theorem, there should be according to mean value theorem, there should be some value, let's call it xi star, where the gradient of this gradient at tangent at xi star matches the gradient of this line segment. So basically, if the tangent at this should be should match this gradient, the gradient of this straight line. That's the mean value theorem. F of xi star squared delta x, right? If you have a continuous function between a to b, if this is a continuous function, you have f of a and f of b. So I can define any number between f of a and f of c, and there'll always be some value c which will be equal to s. I think it's an obvious theorem, like it's trivial, because since it's continuous, there's definitely going to be every value between f of a and f of b will be defined, right? So that means going back here, between f of xi minus 1 and xi, since it's continuous, there will be some value which is defined for the average value. Some value exists, let's call it f of x I star star, which is equal to this. So that means I can write this as, instead of f of xi minus 1 plus f of xi, I can just write 2 times f of xi star star. So basically 2 pi, let's just put root here, delta x. So the sum of all of these line segments, so the sum of all of these line segments will give the approximate value. And if I take n to infinity, I get, so we are finding between a and b, I get this. Well, I initially just wanted to talk about arc length, but I skipped directly into surface area of revolution. So for the arc length, we would have sum of this line segment, this line segment, this line segment, sum of all the line segments, arc length would be sum of the xi squared plus delta yi squared. Xi will be the same across, so this doesn't matter. Then I can take x squared out. And earlier, when we did this, according to the mean value theorem, there exists some value, let's call it xi star, where the tangent at that point is equal to the gradient of the line segment. So let's do this square, and taking n to infinity, I get this for the arc length. Square. Let's see. Yeah, arc length is this.